Okay, so we'll do the following procedure, right? So R prime, oh, and so after you do a few problems for your homework, your hand will start moving like automatically before your brain does. So when you see a vector valued function written as R prime, R of t, you will probably start differentiating without thinking about it, okay? So you take the derivative and then you normalize it because you almost always have to find the capital T. And then you differentiate it and normalize it to find your n, right? So let's do R prime. This is 4t 2t, 8t, okay? And so what is the norm of this? Because I have to divide it by, it's going to be complicated, isn't it? How complicated? Well, it's going to be 16t squared plus 4t squared plus 64t squared. And if you add them up, you get 20 plus 64, 84. And then t squared, let's just assume that t is positive. It doesn't have to be, but for this, it's easier. It is 84t squared, and since t is positive by my declaration here, it's the square root of 84 times t, right? Or you can write, if you are a big fan of factoring out, numbers here, 2 times square root of 21t. All right, so what is my t? That's, well, it's 1 over 2 square root of 21 times t, and then you have 40, sorry, t is in the denominator. Okay, so this is still 1, and t is in the denominator, and then you have 4t, 2t, 8t, and of course, t can be canceled, right? And in fact, 2 can be canceled. Okay, so it turns out this is 2 over square root of 21, 1 over square root of 21, 4 over the square root of 21. Sounds familiar? Yeah, that is constant. Yeah, it's constant. Okay, now why is this constant? Okay, well, that's because I don't know if you noticed this when I gave you this assigned problem here, it is actually a straight line. Okay, it doesn't look like this picture, which I'm about to describe what happens with this curve, because in this case this is not a curve. Okay, it's a straight, R is a straight line, and when you have a straight line, okay, and the speed actually does change, right? Because the speed, of course, I mean, you can tell when t is a big number, this is my speed, and the speed increases linearly with t, right? So it gets faster and faster and faster. But remember, capital T is normalized, so it's going to be, of course, a constant. And it's constant because it doesn't move, okay? It's always, I mean, if I were to graph in this capital T here, it'll be a bunch of unit vectors at every single point, okay? I know that the speed goes faster, but because we are normalizing this, the unit tangent vector stays the same. And so what is n? Well, to find n, you take the derivative of t, right? But the derivative of t is actually 0. So I can't divide by 0. And so n is actually undefined at every single point. That's why I'm, saying that, hey, you should get stuck here because you can't find n because n doesn't exist. Would I ever tell you to solve a question where the answer does not exist? Yeah, maybe. And so you should get used to it, okay? Because sometimes you realize that what you're looking for does not exist. It's such an important lesson in life. But anyway, so that's what, sometimes you just don't have an answer and you have to say the answer does not exist. And so if you have any straight line, okay, any straight motion, the normal does not exist. And I guess it's sort of implicit here because I said the normal vector points inward, right? There is no inward when you have a straight line motion. Okay, if the motion is a curve, just like, here, then your t will be tangent, and of course it's always of length 1, the unit tangent vector, right? And remember what the principal unit normal vector does? It shows you the perpendicular direction inward, like this, right? So the inward is, of course, to the right, to the right, to the right. And then once you have what we call the inflection point, it starts to go this way, right? All right, so what happens right at the inflection point? The inflection point is where the derivative of the tangent, unit tangent, becomes zero. And once the t, capital T, is zero, you cannot divide by the norm of the t prime, t prime, which is zero. T prime is going to be zero. T is not zero here, but the way that the t is moving, it becomes zero. So right at the inflection point, okay, at this point, n is undefined. And so it could just disappear momentarily, like in this case. At any inflection point, capital N disappears. So just keep that in mind. N is not always existing. Sometimes N could not exist at a particular point. All right, so that's that's the second part of our instruction of this section. And so we have covered the arc length and the capital N, the principal unit normal vector. All right, so the third component, or the third part of this, is K. Now this is actually a lowercase kappa in Greek, and this represents curvature. Okay, you can have a bunch of curves, right? So you can have really tiny, kind of a curve here like this. You can have something like this. You can have a straight line, which looks like this, and so on, right? What I want to describe is how curved the curve is. I know it sounds silly. It sounds almost silly to say how curved is the curve, but you can think of this as the way how fast you have to turn the steering wheel if you're driving, okay? So if you're driving on the road like this, this curvature must be big. Okay? I know the curve itself is small, but if you're just driving like this and like this, you have to turn your wheels like very, very quickly, or, and so, okay, the curvature has to be big here. And the curvature is small, that means you are having something almost like a straight line. If the curvature is zero, that means there is no curvature, and that's straight, right? It makes sense, right? That's what we mean by a curvature. Like when you talk about the curvature of a ball pitched in baseball or something, obviously the curvature has to do with how much the object or the path of the ball is curved. All right, so this measures how curved R of t is, okay? But there's something important about this. What am I going to say? What's important is with respect to the shape of the curve, not with respect to t. Right? This is an important point, okay? So let me explain what I mean by this. If you have a curve like this, right, how much of, how curved is this, how curved is this R of t at this point? Okay, and you say, yeah, I mean, it's curved, right? Maybe it's not very big, okay? So we'll try to describe what this curvature is at this point. But it should not be depending on t, because t is just telling you how fast it is. Remember, you can parameterize this curve in all sorts of ways, right? A unit circle can be parameterized by cosine sine, or cosine of 10t, sine of 10t, which will go 10 times as fast. But even if the motion is 10 times as fast, the curvature at any given point should not be depending on the speed. It should only depend on the shape of the curve, right? So that's what I mean by the curvature being defined by s, the shape, and not by the speed, time t. So here's a definition. And I think this makes sense. The curvature should be defined by, how fast, or, okay, so this should be how fast, yeah, by the way, how do you measure curvature? Okay, again, think of t, okay? If t is changed, and of course t is, of course, the length of t doesn't change, it's always 1. So the curvature should be like how fast, as you go along this direction here, maybe with a constant speed of 1, how fast is capital T changing, right? Over here, capital t changes very quickly, but here, not so much. Here, never changes. So the idea of the curvature should be how fast capital T is changing, not with respect to time, but with respect to S. So here's my definition of curvature. Curvature should be dt over ds. Okay, and then we take the norm of this because this is a direct this is the vector. Okay, yeah, that's great. So that sort of conceptually is what we're looking for. How fast is t changing as you go along on that, on that arc, right? This is a great definition. It makes sense, but it's useless. What do you mean by useless? Well, I don't mean it's useless, but it's hard to calculate because we don't use that ds normally, right? So what we will do is we'll separate the top and bottom here. So dt is here and ds. All right, let's try to divide both of these. We do this kind of thing in, chain rule as well. All right, so because we almost always use lowercase t as the parameter, like the time t, so we just divide the top and the bottom by this, dt. Now the top is simply t prime, okay? So you find the norm of t prime, that's the numerator. The denominator is what? Well, we've seen this before, ds over dt, okay? Remember what it's called? It's the change of arc length divided by the time. So this is like distance divided by time, and it is the speed, okay, r prime. All right, so that's how you find the curvature, right? So you can write this as the norm of t prime. Remember, this is not always 1, divided by the velocity, the speed, if you like. And this is what we will use. Use this to find the curvature. Okay, now I will show you 2 different ways to find the same curvature, but this is the one formula that you should know about, okay, for your exams, for your homework. Now for your homework, you have to know a few more, maybe a couple more, just one more different formula for this, okay? All right, so you see what I'm talking about? First, this is the definition that would make sense because we are trying to find the curvature as defined by how fast t is changing with respect to the arc length. Like every time you go a unit 1 length, how fast is d changing? That should define the curvature. But this is not a very user-friendly version of it because we don't use ds. And so we divide the top and the bottom by dt, and the top becomes the norm of t prime, the bottom becomes the norm of v, which is called the speed. All right, so everything is, we have found all of these components. We found capital T, we found capital T prime, we found the velocity and the speed. So we are not really looking for anything new at this point, but we combine T prime, find the norm of T prime, divide it by the speed, and that would be your curvature. All right, now there is another formula for this. So alternatively, you can show, and I'm not going to this, but one can show that the capital T prime, what's in the numerator, this can be written as, and this is some work to do, but if you have to prove this, it turns out it's r prime cross product r double prime. Find the norm of that. You divide it by r prime, and that's of course the speed, cubed, okay? No, sorry, it's squared. So if you can show this, and assume you can, which you can, then the curvature, now imagine all you have to do is to plug this in to the, what you have in the numerator here. And this is of course, yeah, I guess I can put it in here. Maybe that's easier. All right, so what you have on the top is this, okay? So replace that on the top with this expression here. And of course you will have this not square, but another one, all right? And so you can rewrite this thing as r prime cross r double prime. And the reason I'm writing this is because sometimes it's easier to use r prime and r double prime. Remember, capital T could be complicated, and the derivative of T could be very complicated. I'll show you an example of this in just a minute. So if you multiply this and then divide this by r prime, the norm of r prime again, the denominator will be r prime, norm of r prime what? Cubed, right? So here's another example or another formula for the curvature. So I say use this for your curvature. You can also use this for curvature. So this is for your homework. Okay, I'm not going to ask you to, let me just make sure. I'm not going to ask you to use this on your exams. Okay, but some homework problems would require you to use this form. Again, the reason that I want you to know this formula as well is because sometimes T prime could be terrible looking, could be horrendous. And so sometimes this is much easier to use. Okay. I will give you just another version of it, even though you will probably not be needing this. If y happens to be the function of x, okay, and this is something sometimes students learn in calculus too. If y happens to be a function of x, now, we are not talking about this now because we have a vector valued function parameterized by t, but if f happens to be a function of x, y happens to be a function of x, then the curvature can be written as, and this is really similar to the second version I gave you, it is the absolute value of the second derivative of f, and then in the denominator, instead of this r prime, you have 1 plus f prime of x. That's, sounds like an arc length parameter, and then you multiply this or raise it to the 3/2 power. It is the same thing. You do not need this. But if you are looking at some calculus book or something, you may encounter this. It is the same curvature, okay? It's just only if this is the case. And by the way, here you can write this as x, f of x, 0. That's your vector valued function. If you just use this notation and try to plug everything into this r prime and r double prime, you will get this. Okay, but as I said, you don't need to know that. All right, let's do an example, and we will find out the curvature of something quite familiar. All right, find the curvature of the circle of radius 1 is kind of boring. Let's say radius a, okay, where a is some constant. Okay, so a is a circle. Let's go ahead and do that again. A is a circle of radius. This is a circle of radius a. Now, of course, the curvature does depend on a, right? Think of a small circle, right? Think of a very small circle here. Okay, what do you think the curvature is? Okay, here you can assume that the curvature is bigger here, right? And here the curvature should be small. Why is that? Well, because if you're going around this small curve, you're turning very quickly. If you're going around this big curve, then you are going, your steering wheel is not like turning extremely to the right or to the left. So that's the assumption. So the size of the circle should be sort of inversely proportional to the curvature at every given point. Okay, well, let's try to verify that. I can parameterize the circle how? A cosine t, A sine t. Remember, because you want x squared plus sine squared to be equal to, you want x squared plus y squared to be equal to a squared, right? So you put a here as the radius, and that should be your coefficient. Okay, r prime is equal to negative a sine t, a cosine t. All right, so what is your t? Oh, I need to find the norm of this, which is, of course, I guess you can write, you know what this is, right? It'll be a square sine square plus a square cosine square under the radical, which is just a. Okay, so you divide this by a, and it will be negative sine t cosine t. I hope you're okay with this, right? Basically, you're trying to find the unit vector in the direction of the velocity r prime, and basically that amounts to dividing this by t. Okay, so what's t prime? T prime is negative cosine t sine t. So negative sine t. All right. Now you have a formula here. The first formula will work quite well here. Try to finish this problem up and find the curvature. And I also want you to apply this second formula. All right. So this is a formula, first formula. This is your second formula. Try to apply both of these and see if you can get the curvature of the circle of radius A twice, okay? And the answer should be, of course, consistent, both the first and the second time. All right, so when you do that, come back and then we will go into the next segment of this lesson video.